Hey everyone. So today we're going to get into another way to find the area under the curve. So this is lesson 4. You will recall last lesson we dived into Riemann sums, okay? And Riemann sums was a way that we could use limits and creating an infinite amount of rectangles, and we created this formula that would help us get the area under the curve. Today we're going to look at the exact same sort of concept, finding that area, but in a much probably easier way, and actually something that's super, super cool. If you ever sit and say to yourself, why do we even care about antiderivatives? Why are you making me do this? Well, buckle up and let's find out. Okay, so the area under y equals f of x from x equals a to x equals b is the area above the x-axis and under f of x. Now, it's to the right of the vertical line x equals a and to the left of the vertical line x equals b. Okay, now, based on that definition, I want you to note that the area at a would be 0. Why is that? Because at A, we would not have essentially started the rectangle yet, right? Remember how Riemann sums was creating all those rectangles? Well, when I'm right at my starting point, there is no rectangle to draw yet. I have to start moving in order for the rectangle to actually come up. So the area under the curve at the place that I start is 0. That's a super important point that will come up as we develop some theorems here, okay? Okay, so let's revisit our function. This is the exact same one that we dealt with yesterday in Riemann sums. F of x equals 3x plus 2 and the trapezoid form. We're going to look at a equals 1 to b equals x. So I know that in our example yesterday, we did a 3 there. Right now, I'm just trying to get a little bit more of a general formula going, okay? So I'm going to call that spot x so that we could actually stop it whenever we want to. Okay, so we know that the area of a trapezoid is 1/2 times the height times base 1 plus base 2. Now, just for clarification on a couple things, if you recall from yesterday, what we talked about was this was actually the height, right? So in this example, I'm going to call the height x minus 1. Then base 1, well, that would be this y value right here, but can't I call that y value f of 1, right? Base 2, I can call that y value f of x. Okay, so I'm actually going to start with a higher one. It doesn't really matter, but I'm going to go f of x plus f of 1 instead of f of 1 plus f of x. Totally doesn't matter though. So if this is the area of the trapezoid, I can now say that this would be the area in this context. Now we're just going to call it the area of x, where x is I'm inputting where I want to stop. Okay, so if this legit had been 3, I would say the A3 here. But because I'm stopping at x, I'm calling it AX. Okay, so it's 1/2 h base 1 plus base 2. So h was x minus 1. And then I have my base 1 and base 2 as f of x and f of 1. Okay, well, I know what f of x is. F of x is 3x plus 2, so I can plug that in. I know what f of 1 is because I can just plug 1 in for x. So that's going to give me 3x plus 2 plus 5. Okay, plugging 1 in for x gives me 5. F of 1 is 5. All right, so now I'm just going to clean this up a bit. This is 3x plus 7, and I can distribute this. Okay, so then FOIL this out and multiply everything by 1/2. And I end up with ax equals 3x, or 3 over 2x squared plus 2x minus 7 over 2. Now, that represents the area from 1 to x. This formula creates the area. But remember, because I had x here, I can stop whenever I want. So this is a general formula for the area under the curve, starting at 1 and heading to whenever I want to stop. Okay. Okay, so the area is 3 over 2x squared plus 2x plus 7 over 2. Okay, so now I'm curious, what is the derivative of ax? Well, 3 over 2x squared. The 2 comes to the front. That would give me 3x plus 2. The derivative of a to the ax, is 3x plus 2. Well, everybody getting excited? Whoa. So, let me take my ink off here. The derivative of a is 3x plus 2, and little f of x is 3x plus 2. So the derivative of a is little f of x. So that is the derivative of the area is equal to the curve. The derivative of the area of the curve is equal to the curve. Or the area is the antiderivative of the curve. Okay, the area is the antiderivative of the curve. That's exciting. Okay, the area is the antiderivative of the curve. So determine the area under the curve, f of x equals 3x plus 2, and above the x-axis on the interval 1 to 3. So here we go. We know that little f of x is 3x plus 2. I'm going to figure out the antiderivative. Okay, so I'm going to get the exact same thing I just got. I'm just showing you now how I would do the question without leading you the way I led you. Okay, so if I go to get the antiderivative, I need a 2 up here. So this will be 3 over 2 x squared plus 2x plus c. Okay, and now I'd have to figure out c. Well, in order to figure out c, I need an initial condition. Do I have an initial condition? I do. Remember that I said my starting area was 0. So I know that a of 1 is 0. Okay. So if I plug in 1 for x and 0 for y, I can solve for c. And when I do that, I end up with that negative 7 over 2. And so I have an equation of the area equation is 3 over 2x squared plus 2x minus 7 over 2. Okay. Which is the same equation I just got, but this time I'm doing it without developing it. Okay. All right. So look familiar. This was the function, just like I said, which finds all the areas under the curve from 1 to x. Okay. So now the area from 1 to 3 is a3. So I just plug in 3 for x. And what do I get out? I get out 16. Which is exactly what I did when I just did the trapezoid formula yesterday, which is exactly what I did when I went through the whole Riemann sums process yesterday. So now, this new process, I'm getting the exact same answer. Okay, and what did I do? I took the antiderivative, and at the moment, I had to figure out my initial condition. I'm going to get rid of that in a second for you, but at the moment, I had to figure out my initial condition to get the equation. And then I could just plug in my final x value, my right bound x value, in order to get the area. Okay. Okay, so let's switch things up and go to a new equation. Now we're going to look at the area under the curve for f of x equals 2x squared plus 3, and above the x-axis on the interval from 1 to 4. Okay, 1 to 4. So the first thing we want to do is take the antiderivative of 2x squared plus 3. Well, if I do that, my 2 on the x squared becomes a 3, so I end up with 2 over 3 x to the 3 plus 3x plus c. Okay, so now I need to figure out what c is. In order to figure out what c is right now, I need some sort of initial condition, and for that, it's that a of 1 is 0. So I plug f of 1 is 0. So I plug 0 in for my y value, 1 in for my x value, and I solve for c. Okay, when I do that, I end up with c equals negative 11 over 3. And so now I know that my equation for the area is represented by 2 over 3 x cubed plus 3x minus 11 over 3. Now I need to find a 4. So I'm going to plug in 4 for x. Do the math, and I end up with 51 units. Okay, 51 units squared. Okay, so now what we want to do is rid ourselves of that pesky little c. Think about this for a second. We said that the original curve is y equals f of x, and we said that the area will be the derivative of the original curve, so big F of x plus c. But we also said that a of a is 0. Remember that comment right near the beginning of this lesson. At the place where we start at that initial x value, the area is 0 because we haven't had any movement yet, okay? So the area at the starting point is 0. So that means if I looked at f of a, okay, I know that when I input a, I'm going to get out 0. Well, if that's the case, then I can represent c as negative f of a, right? I just bring my f of a over. And so instead of writing the area will be f of x plus c, I can actually say, hey, I can put that right there. So the area is going to be f of x minus f of a, f of x minus f of a. So essentially, it's the right bound minus the left bound. Okay, so by substitution, we have the following. I'm just going to clear that ink for you. So we say the area at x will be f of x minus f of a, or the area at b is f of b minus f of a, depending on whether we're talking about the area from a to x or whether we're talking about the area from a to b. Essentially, I need you to see here that the area is calculated by going f of the right bound minus f of the left bound, okay? So to determine the area under a curve, determine the antiderivative of the function and evaluate it from right bound to left bound, okay? Now, what does that look like? Well, visually, it essentially looks like this. Well, remember that we said that the area is, the area that we're looking for is the area that's underneath the curve and above the x-axis, okay? So f of b, the area there, would be underneath the curve and above the x-axis all the way up to where b is, okay? Then f of a would be the same thing, the area underneath the curve and above the x-axis all the way up to where a is. But then I'm subtracting f of a, okay? So if I end up subtracting f of a, what I get is the area under the curve and above the x-axis between the points a and b. That, my friends, is what we call the fundamental theorem of calculus. I feel like when I say the fundamental theorem of calculus, like thunder should clap or something, but maybe in a future video, I will voice over anyway, never mind. Okay, the fundamental theorem of calculus. Okay, so here's what the fundamental theorem of calculus says. If f of x is continuous on the interval from a to b, then the integral of f of x from a to b will be the limit as n approaches infinity of f of x subscript I, increment of x, when I is 1 to n, where the increment of x is b minus a over n, and x subscript I is a plus the I times the increment of x. Now, before you all shut down on me, that is Riemann's sums. Riemann's sums, not Riemann's thumb. It's Riemann's sum. Right? We talked about that yesterday. Alternatively, now we can look at it as the integral of f of x from a to b would be the antiderivative of f of x from a to b, which would be the antiderivative of when x is b minus the antiderivative when x is a. Okay, so big F of b minus big F of a, where big F is any antiderivative of f. Okay, so this guy was Riemann's sum. Sorry, I lost my ink. That guy was Riemann's sum. This guy is now what we can deal with. Okay, and that's a much nicer formula to deal with to get to the same thing. Okay, so for the special case of f of x being greater than 0, the integral of f of x on the interval from a to b is equal to the area under the curve y equals f of x from a to b. So the area is the integral of f of x from a to b, which would be the antiderivative from a to b, which would be the antiderivative with an input of b minus the antiderivative with an input of a. This is called the definite integral. Remember, when we started all this, we were calling it an indefinite integral because we had that c there, and c could be anything. Now it's the definite integral because the answer is an element of the real numbers. Okay. Okay, so a few notes. The integral of f of x from the interval a to b is defined even when f of x is not greater than 0. And we're actually going to talk about that in just a few examples. A and b are called the limits of integration, the lower and the upper limits respectively. F of x is called the integrand. And then the symbol, which we talked about earlier, should be regarded as a single symbol, right? And then the f of x goes in between. None of the pieces can be taken away. Notice how the parts correspond to the Riemann sum formula. And the process of calculating an integral is called integration. Okay. Now, some properties that you want to get used to, and again, these will look familiar to you. They're very similar to the limit properties that we talked about. So the integral of f of x from a to b will equal the negative integral of f of x from b to a. Okay, so if I reverse the direction, I would just end up with a negative number. Okay, the integral of f of x from a to a would be 0, and we've actually already talked about that because we talked about the fact that our initial is 0. Okay, the integral of a constant in front of f of x on the interval from a to b, we can put that constant in the front. Okay, and multiply the constant by the integral instead of taking the integral of the function times the constant. Okay, so it doesn't matter where that constant is, whether it's with the integral or in front of the integral, you'll get the same answer. The integral of f of x from a to b also equals the integral of f of x from a to c plus the integral of f of x from c to b. So you can use a point in between a and b, and then set it up that you add the two pieces together. Now, you may ask yourself, why would you ever do that? Stay with me. We'll talk about that in just a couple minutes as to why we would do that. And the integral on the interval from a to b of two functions being added together is the same as taking the integral separately and then adding those together at the end. Okay? Awesome. Determine the area under f of x equals 2x squared plus 3 from 1 to 4 bounded by the x-axis. Okay, so the first thing we're going to do is we're going to say the area up to 4 would be the integral of 2x squared plus 3 from 1 to 4. Now, what that means is it's the antiderivative from 1 to 4. So I need to figure out the antiderivative. Then I'm going to plug in 1, I'm going to plug in 4, I'm going to subtract those two guys. Okay, so the antiderivative, the 2 became a 3, 2 over 3 x cubed plus 3x. That will be the antiderivative. So I figure out what f of 4 is, and then I subtract what f of 1 is. So f of 4 would be, sorry, my head is in the way of my slide. So I'm going to calculate the area of 2/3 x cubed plus 3x from 1 to 4. So I plug in 4, I plug in 1, and I subtract those two numbers. Okay. Do you see what I'm doing here? Okay. So I said I was taking the integral first. It's all about communication. Then I said I established what the antiderivative was. So then once I've established what the antiderivative was, that's that big F, I can say that the area 4 will be that from 1 to 4. Okay, so then I plugged in 4, to get an answer, and I plugged in 1 to get an answer, and then I end up subtracting them. So I should get 51 units squared there. Okay, 51 units squared. All right, let's try again. Let's do f of x equals 1 over x, and I want to go from 1 over e to e. Okay, 1 over e to e. So first thing I'm going to say is the area of e will be the integral of 1 over x from 1 over e to e. That'll be the antiderivative from 1 over e to e. Okay, so I have to figure out what the antiderivative is. Big F of x. Well, big F of x, if little f of x is 1 over x, that means I needed to have been, the antiderivative of that needs to be ln of the absolute value of x. Okay, ln of the absolute value of x. So now what I'll do is I'll say that the area with an input of e will be essentially ln e minus ln of 1 over e. Okay, so it's ln x from 1 over e to e, which is ln e minus ln 1 over e. Ln e is 1. Ln 1 over e is -1, so I end up with 1 minus -1, which is 2. Okay, so the area with an input of e will be 2. Okay, all right, determine the area under f of x equals cos x from 0 to pi over 3. So again, I need to figure out what the antiderivative of cos x is. Okay, and that would be sine x. So a at pi over 3 will be the integral of cos x from 0 to pi over 3, which will be the antiderivative from 0 to pi over 3. The antiderivative is sine x. So essentially I'm looking at a of pi over 3 will be sine of pi over 3 minus sine of 0. Okay. The sine of pi over 3 is root 3 over 2. So I have root 3 over 2 minus 0, which is root 3 over 2. Okay, so the area at pi over 3 would be root 3 over 2. Okay, good. Now, this one gets a little trickier. Use the definition of the definitive integral to evaluate the following. Okay, so the definition of the definitive integral will be the integral of that from 0 to 5 will be the antiderivative from 0 to 5. So I know that the integral at 5, the area at 5, sorry, will be the integral of 3x minus x squared from 0 to 5, and that'll be the antiderivative. Well, what's the antiderivative of this? The exponent on this x will become a 2, so this will become 3 over 2. The exponent on this x will become a 3, so this will become 1 over 3. So when I go to take the antiderivative of that, I end up with -1 over 3 x cubed plus 3 over 2 x squared. Now, if I want a5, that means I'm looking at f5 minus f0. So I'm going to take my antiderivative and I'm going to evaluate it from 0 to 5. Okay, so that's f of 5 minus f of 0, which is what I just said. Okay, and you're just going to do the math on this. And you end up with -25 over 6. Now here's where that conversation lies. Why the heck do we get -25 over 6? Okay, why is the value negative? And the short answer is we need to take a look at what this function looks like. Okay, so let's sketch the graph of y equals 3x minus x squared, labeling all the intercepts. Shade in the area bounded by y equals 3x minus x squared, the x-axis and the vertical lines, x equals 0 and x equals 5. Okay, so I've done that for you. This is the graph of 3x minus x squared. Now, if I'm looking at from 0 to 5, I've put in vertical lines for 0 to 5. And now you can see my problem right away, okay? When I shade this in, some of the shading is actually above the x-axis and some of the shading is below the x-axis. And so what happens is the shading that's above the x-axis ends up being positive and the shading that's below the x-axis ends up coming up as negative. okay? The fact that I got a negative answer then means there's more shading below the x-axis than there is shading above the x-axis, okay? So here's what we're gonna do. Use antiderivatives to determine the shaded area that is above. So the shaded area that is above would go from 0 to 3. So instead of evaluating from 0 to 5, I'm just gonna evaluate from 0 to 3, okay? And I knew 3 because I knew if you look back at your original equation, the zeros were at 0 and 3, right? I could factor out an x and it would be x times x minus 3, okay? So if I just look at A3, so that would be f of 3 minus f of 0, and that's going to get me 9 over 2, okay? Then I'm going to look at the next one. The next one would be from 3 to 5, so that means I'm going to look at f of 5 minus f of 3. Okay, so the portion that's below the x-axis would be f of 5 minus f of 3, and that would give me negative 26 over 3. So the first statement that we have is, where does that negative 25 over 6 comes from? Well, it's actually those two pieces added together. Okay, 9 over 2 plus negative 26 over 3 gives me that negative 25 over 6 that I originally got. Okay, now that would be considered what we call the net area. So it's the positive and the negative added together. We also sometimes want what we would call the total area, which would just be how much is shaded. I don't care whether it's above or below, I just care whether it's shaded, okay? Well, in this instance, what I would do there is, there's a couple things I could do. Either I could subtract the negative value, or I could look at it as adding the absolute value. It doesn't really matter which one you do, just whatever makes the most sense in your head. Okay, so what I did here is I subtracted the negative if I wanted the total area under the curve. And so the total area would be 79 over 6. Now, what you have to be careful of then is there are two different areas that we can get. There are two different answers that I can have. One was negative 25 over 6 and one was positive 79 over 6. The negative 25 over 6 refers to the net area, and the 79 over 6 refers to the total area, okay? So we need to be careful. There's a difference between evaluating and finding an area. That first question where I got the negative 25 over 6, that was evaluating, not finding the area. So when we are asked to evaluate an integral, we are finding the net area. That is, we could be adding both negative and positive values together. But when we are asked to determine the area, we want to be finding the total area. If there are any negative areas, we subtract them to make them positive, or you could look at it as you're adding the absolute, whichever makes most sense to you there, okay? Okay, now, if you're curious about how to do this on a graphing calculator, I've given you some Casio notes and some TI notes, okay? And you can actually, just if you're checking your work at home, this is how you could check your work, okay? Okay, so in general, if a function f takes on both positive and negative values, then we can interpret the integral of f of x from a to b as a difference of areas. And so what we would say is the integral of f of x from a to b would be area 1 minus area 2, where area 1 is the positive area and area 2 is the negative area. Okay, so the region below the x-axis. And so because we're subtracting A2, we end up subtracting a negative, and so we add that on, and that's how we get the total area, okay? Okay, last example for today. Determine the integral of x cubed on the interval -1 to 2 and interpret the value as a difference of areas. Use a diagram to illustrate your interpretation. So if I'm looking at f of x equals x cubed, I want to think there for a second, where do I change from being underneath the x-axis to being over above the x-axis, right? Because if you think about that, you all know that x cubed would look like this, right? So it's right here that I change from being below to being above. If I'm going from -1 to 2, let's just say -1 is there and 2 is there, okay? you can see that I'm going to have this little piece there that will be below, and I'm going to have this piece here that will be above. Okay, so you have to kind of have a visual of what these graphs look like in order to have a good assessment as to where you break it up. Okay, now that means I'm going to have to break this up from -1 to 0, and then also from 0 to 2. Okay, so the antiderivative will be the 3 comes up to be a 4, and then that means I end up with 1 over 4 x to the 4. Okay, and so I want to look at the first guy. I went from -1 to 0. Okay, so -1 to 0, the integral of x cubed is 1/4 x to the 4, and I'm going to evaluate that from -1 to 0. So I plug in 0, I plug in -1, and I figure that out, and that gives me an area of -1 over 4. Okay. Now I'm going to have the same conversation, but instead of going from -1 to 0, I'm going to go from 0 to 2. Okay. I'm going to pause so you can pause. Okay, and what you should have gotten there was 0 to 2, I ended up getting an area of 4. Okay. Now take note, I called my negative area a subscript 2, and I called my positive area a subscript 4, because the formula we just talked about, it's going to go the positive minus the negative, and by going minus the negative, right, it was a1 minus a2, where a2 is always the negative one. By going minus the negative, we're adding that to get the total area. Okay, so 4 minus -1/4 is 17 over 4. So I have a total area, not a net area. We're not evaluating, we wanted the total area. Okay, the total area is 17 over 4. Okay, so that's what we're doing today. Here is your mission, and make sure you give yourself some time to do it. This one is broken down. You will see as you go through these pages, at some point you get into more practice. That set, the next kind of day in class is a work period for you to do that, okay? So this particular lesson, I'm giving you 2 class periods to do. Some of you may want to use that second class period as well, just to catch up on some of the Riemann sums stuff that we did prior as well, okay? So you'll have 2 lessons in class to do this, and then we'll pick it up and look at, what are we looking at next? Area between curves, okay? So that'll be the next guy. All right. Talk to you guys soon. Take care.